Good morning. So yesterday we were discussing the function of the d orbital of phosphorus. Nitrogen doesn't have the d orbital, but phosphorus has the d orbital. One of the three electron can be promoted to d orbital. So it can now exceed its covalency beyond 4. But nitrogen cannot exceed its covalency beyond 4. So nitrogen can show maximum covalency 4 as in the case of NH4 plus. But phosphorus can exceed its covalency beyond 4. So phosphorus can form pentahalides, for example, PCl5. But NCl5 is not known, or NF5 is not. Maximum covalency nitrogen can show is 4 because it has got 4 orbitals available for bonding. In the case of phosphorus PCl5, it has got again vacant p orbitals, so it can exceed PCl6 minus, that is also possible. PCl6 minus, that is also possible. Covalency means the number of orbitals available for group formation. Oxidation state means the number of electrons available for donation. So, oxidation state of nitrogen can be +5. In presence of an electronegative, no electronegative, nitrogen can give all the 5 electrons. But NCl5 is covalent bonding. It is not there because nitrogen doesn't have those 5 orbitals. Maximum it can have 4 orbitals. Now, nitrogen can form p-pi bonding as in the case of N, triple bond N. Nitrogen can form p-pi bonding, while phosphorus can form p-pi bonding. D-pi, D orbitals and p orbitals for the next sidewise overlap. But in this case, d pi p pi is not possible because nitrogen doesn't have d orbitals. So nitrogen cannot form d pi p pi bonding, while phosphorus can form d pi p pi bonding. Phosphorus can form d pi bonding also. This is of phosphorus, and the next atoms d-pi. So nitrogen can form d-pi bonding, d-pi p-pi bonding, but sorry, phosphorus can form d-pi p-pi bonding and d-pi bonding also, but nitrogen cannot form d-pi p-pi bonding. Why? Because nitrogen doesn't have d. Consider R3N triple bond group and R3P triple bond group. This is an existing, this is a well-known compound, but this does not exist. You see, around nitrogen, you count 5. It's not possible. Around nitrogen maximum. R3N double bond O is not existing, not possible. R3P double bond is possible. Around phosphorus, 5 bonds allowed, possible. But around nitrogen, 5 bonds are not allowed, or it is not possible. Nitrogen can maximum form how many bonds? 1, 2, 3, 4. 4 orbitals. Maximum it can form 4 polar bonds. R3 double bond O is possible, while R3 and double bond O is not possible. Phosphorus can form bonds with transition metals. For example, phosphorus as a ligand, CH3. Phosphorus. This pair of electron can be donated to making the orbitals of transition to form a sigma bond. At the same time, from the transition metal, from the filled d orbitals, it can give electrons to vacant d orbitals of phosphorus. That forms a pi bond. So phosphorus can make using its d orbitals. That means d pi bond. Transition metals d orbital, phosphorus d orbital. So d pi bonding. By sidewise overlapping of d orbitals, one is of transition metal and one is of that phosphorus. So phosphorus has d orbitals, it can make use of its d orbitals to form d pi bonding. Now, NCl5 halix, right? Produce halix, and 15th group's halix, NCl5. PCl5 is existing while NCl5 is not existing. That means all are in this plus 5 condition. B plus 5, BCl5 does not exist because B5 is very unstable. B5 changes to Bi. Bi5 changes to Bi3 due to inert pair effect. Or you can say Bi5 is a good oxidizing agent. It will change to Bi3 plus from Bi5 plus. And PCl5 is a compound, but Pi5 does not exist. Why? Because I atoms are so big. So these 5 big I atoms are not held by the center phosphorus. Phosphorus compared to this I, phosphorus is very small. The small phosphorus cannot hold all those big 5 I around it. So Pi5 does not exist. NCl4 and Ni5 does not, these things do not exist by the cycle, cannot exceed this covalency beyond 4. Maximum item can show what covalency 4 plus in the case of NH4 plus. So halides, pentahalides, these are the possibilities of pentahalides. Remember, nitrogen covalency is maximum 4, but phosphorus can exceed its 4. So here is the inert pair. Bismuth 5, bismuth Cl5 or bismuth I5 does not exist because it is not a stable oxidation state. What about phosphorus? Phosphorus oxidation state, that is H3PO3 on heating, it will be changing to H3PO4 and H3PO4 and now here in H3PO4 it is plus 5 and in this state it is minus 5. So the same oxidation state is undergoing oxidation as well as reduction. That means H3PO3 undergoes disproportionation. By the addition, H3PO3 undergoes disproportionation. How? Or what happens when H3PO3 is heated? By the addition like this. What happens when H3PO3 is heated? It disproportionates, and we have to give this equation also. What are the reactions with metals. With metals, nitrogen forms, for example, Mg3N2. Phosphorus forms Mg3P2. Similar. Mg3, Mg3N2, magnesium nitride, or Mg3P2. Valency of magnesium is 2, valency of nitrogen is 3. Similar is the KCl. So Mg3N2 and Mg3P2. Here, Mg is the metal. With calcium, similar that is Ca3. Ca3P2 is important for us because Ca3P2 on reaction to water forms H3 and CaOH. P3 is a poisonous gas. The warm front you must have seen black smoke type gases, that is P3. Ca3P2, you put water on, you sprinkle water on the Ca3P2, immediately thick black smoke, lots and lots of thick black smoke will be fuming, and that is used as a smoke screen. Smoke screen. So, to cover the view of these enemies, the smoke screen is utilized. So Ca3P2 plus H2O gives 3Ca plus 2PS3 plus PS3. So this reaction is important. By sprinkling water on Ca3P2, lots and lots of PS3 will be coming out, which is used as a smoke screen to cover the vision of the enemies. Next, hydrides of 50. So PH3 is a hydride. Mg3N2 plus H2, similar, that is MgOH plus NH3. NH3 is a hydride of nitrogen, PH3 is a hydride of nitrogen. Similarly, you can see other hydrides of nitrogen, and hydrides of this NH3, PH3, NSH3, HBH3, BIH3. We have to learn a lot about this hydrides. First is bone diagram. Bone diagram, all are pyramidal shape. You see, as the size of the atom increases, the bond length is also increasing. What about the bond diagram? This pair of electron is more closer towards nitrogen because of the high electron nitrogen. So there is electron repulsion. So here, electron pair is more closer towards nitrogen. So there is electron pair repulsion. Electron pair repulsion. So the bond angle is maximum in the case of ammonia. Bond angle is minimum. You can see I have drawn in such a way. Bond angle of BS3 is the least. Why? Because the least electronegativity. So that's about the bond angle. Bond angle. Now, Basic character. Number 2. Basic. Basic. Ammonia is the highest basic because the size is smaller than its lone pair. Now I am showing this lone pair. Which will give this lone pair? We know that ammonia is always basic. Which will give this lone pair very easily? Ammonia. Because electron density is concentrated on the small size ammonia. But in the case of bismuth, BiH3, BiH3 size is bigger. So that pair of electron is diffused in this bigger structure. But here, this is concentrated. This I will show you more apart. This is more apart. This will be more apart. So here it is diffused. In the case of ammonia, that electron density of nitrogen is the dense, that is concentrated. So, like ammonia can give this pair of electron very easily. Most basic one is bond angle. Bond angle is greater for ammonia than BH3, then ASH3, then SBH3. Bond angle NH3, then PH3, then BIS. What are the basic character? Same pattern. Ammonia is the most basic. So NH3 is 3, ASH3, SBH3, and BIS. Number 3, thermal stability. Thermal stability. That's on heating, whether it will break easily or not. On heating, if it breaks easily, then it is thermally unstable. On heating, if it breaks easily, then we say it is thermally unstable. Thermally unstable. So which will break easily? Where the bond length is more. Where the bond length is more, this bond will be broken easily. Is thermally unstable. So which is the most stable? NH. NS3 is the most stable. So PH3 same branch. SH3, SBS3, SBS3, and BIX3. Now, next, which is the best reducing agent? Which can give H very easily? Which is the best reducing agent? Which is the best reducing agent? Means which can give? Which is the best reducing agent? That is, which can easily give out H. Which can easily give H? That is BAS3. It will be breaking very easily. So here BIX3 first, then HBS3, then ASH3, then PH3, then NH3. Reducing character. Next, boiling point. Boiling point. Boiling point, and means as the size increases, van der Waals force of attraction between these molecules will be increasing. So, as the size increases, boiling point also increases. As the size increases, boiling point also increases. Means I am writing the boiling point 290, 290, 254. 290, 254, 210. It's increasing. In this way, it is increasing to 10, 185. See, 185. Then size increases to 10, size increases to 54, size increases to 90, but here it is 238. 230. Why there is high boiling point? Of course, you know, in the case of ammonia, you see nitrogen, NOF can form hydrogen bonds. So, in the case of ammonia, there exists hydrogen bonding. So, to break this hydrogen bond, we have to supply heat energy. So, this is coming in between. It is coming at the center. It is coming at the center. So here, boiling point highest is for BiH3, then HBS3, then ammonia, then ASH3, and the least one is only here in boiling point we have to take care that ammonia is coming in between. Formation of trihalides. NF3, NCl3, NBr3, Ni3. Formation of trihalides. You see, NF goes N is small, F is small. N is small, but Cl is big. It will not bigger. N is small, then Br is bigger. N is small, and I is again bigger. Bond is the most stable one. That is similar. Bond between the similar size is the most stable. So NF bond is more stable. So here NF3 is a stable compound. NF3 during the formation of NF3 is a stable compound means during the formation of NF3 from nitrogen and fluorine. Lot of unavailable believes that's why NF3 is having less energy or it is stable. The question is, NF3 is an exothermic compound while NCl3 is endothermic. And the question, NF3 is exothermic while NCl3 is endothermic. Why? During the formation of the stable NF3, its lot of energy is released and the product formed NF3 is having very less energy, that is more stable. This is due to what? Due to means this is both N and F are small. They are of similar size. Bond between similar size is more stable. So this is due to the small size of N and F. So bond between N and F is strong due to the same size. NF3 and NS3, the previous NH3, which is more basic? After that, we come to the structure. NF3, NF, F, F. N, H, H, H. Which is more basic? Basic means no one is comparing with hydrogen and halide. Which is more basic? Basic means which can donate the pair of electron very easily. Which can donate the pair of electron very easily. See, fluorine is highly electronegative. All the three fluorides will be electron density towards that. So this pair of electron cannot be given out. But here, electronegativity of hydrogen is very less. So NH3 is more basic. This is more basic. So here, comparison questions will be coming, comparison questions. Which is more basic? Last year we learned the bond angle. We compared the bond angle of NF3 and NS3. Here, this year, what we are learning, the basic character, which is more. N of 3, coming to this N of 3 and P of 3, P of 3, PCL 3, like that. Say PCL 3, PBR 3, or PI 3. This PF3 can act as a Lewis acid also. All are having, they can act as Lewis base at the same time they can act as Lewis acid also because P has vacant orbitals. P is PF3. PF3. Here PF3 has got vacant d orbitals to the vacant d orbital, it can accept pair of electrons. But NF3 cannot. NF3 neither nitrogen nor fluorine has d orbitals. Nitrogen has no d orbital. Fluorine also has no d orbital. So no electron pair can be taken from outside. But in the case of PF3, it can PF3 phosphorus has d orbitals. Phosphorus has d orbitals. Not only that, due to this high electronegativity of fluorine, that phosphorus d orbital can easily accept that pair of electrons. So they can act as Lewis acids also. Rest we'll do in the next class. Thank you.